Welcome to The Explainer. You hear it all the time, right? Our planet is changing. But what does that actually mean? Today, we're going to cut through the noise and look at the actual science. We'll break down how human activity is reshaping everything, our atmosphere, our oceans, and the land itself. All right, so here's our game plan. We're going to walk through our planet's major systems to see the whole picture. We'll start up in the air, then dive deep into the oceans, and then check out what's happening on land. Finally, we'll tie it all together with the hard evidence and take a peek at what the future could look like. Let's just start with this. This is a huge statement from the IPCC, which is basically the world's top authority on this stuff. In science, words are chosen really carefully. And unequivocal, that's a heavy hitter. It means the evidence is undeniable. There's no room for doubt. This one word really sets the tone for everything we're about to see. And that brings us to this word. It might look a little technical, but it's at the heart of our entire discussion today: anthropogenic. All it means is that something was caused by humans. And this is so important because it's the key to understanding that what we're seeing isn't just some random natural thing happening. Nope, this one's on us. So let's start from the top. Literally, our first stop is the atmosphere. Think of it as this invisible blanket of gases that keeps Earth cozy and makes life possible. But as you're about to see, we've been making that blanket a whole lot thicker. This right here gets to the core of it. The greenhouse effect, by itself, is a good thing. It's totally natural. Without it, Earth would be a frozen rock, about 30 degrees Celsius colder than it is. The problem, the real issue here, is the enhanced effect. We're pumping extra heat-trapping gases into the air, turning that nice, cozy blanket into a thick, heavy duvet that's trapping way too much heat. So what are these extra gases we're adding? Well, this chart lays out the main players. As you can see, carbon dioxide, or CO2, is the biggest chunk of the pie. Now, other gases like methane are actually more powerful at trapping heat in the short term, but the reason we're so focused on CO2 is its staying power. It just hangs around in the atmosphere for centuries, so its warming effect just keeps building up over time. And this timeline really shows you what that buildup looks like. For thousands of years before the Industrial Revolution, CO2 levels were pretty stable, right around 280 parts per million. But then, boom, look at what happens after 1750. That line doesn't just climb, it goes nearly vertical. It's a massive acceleration. By 2012, we'd hit 396 parts per million. And you might be thinking, okay, is that a lot? Well, on its own, it's just a number. But when you add some context, well, that's when it gets wild. Let that sink in. Scientists can look at ice cores to see what the atmosphere was like in the past, and the data is crystal clear. There is more CO2 in the air right now than at any point in the last 800,000 years. To put that in perspective, our species, Homo sapiens, has only been around for about 300,000 years. We are way, way off the map here. Now, warming isn't the only side effect. Other emissions, mainly from burning coal and from car exhaust, create a whole different issue. These pollutants get swept up into the atmosphere, mix with water in the clouds, and then fall back to Earth as acid rain. And the crazy thing is, it can damage a forest or a lake hundreds of miles away from where the pollution started. And you know, our impact isn't just about dumping new stuff into the atmosphere. It's also about what we're breaking. Way up in the stratosphere, we have this thin, fragile ozone layer. Think of it as Earth's natural sunscreen. It blocks the most dangerous UV radiation from the sun. Without it, we'd be facing a lot more than just a bad sunburn. Okay, so all of that extra heat and carbon that's building up in the atmosphere has to go somewhere. A huge amount of it gets absorbed by the oceans. The sea and the sky are constantly trading energy and gases back and forth. Just look at that number. A staggering 80% of the extra heat trapped by our thicker atmospheric blanket has been soaked up by the oceans. They've acted like a giant heat sponge, which has actually slowed down the warming we feel on land. But that comes at a huge price. For one, when water gets warmer, it expands. That thermal expansion is a major reason sea levels are rising. But that's not all. Because when the ocean gulps down all that CO2, it sets off a chemical reaction that makes the water more acidic. Now look, it's not going to turn into a vat of acid or anything, but that tiny drop from 8.2 to 8.1 on the pH scale is a massive chemical change on a global scale. And as you can see, that trend is expected to speed up. So why should we care about a tiny change in ocean chemistry? Well, that more acidic water makes it much harder for creatures like corals or oysters or even tiny little plankton to build their shells and skeletons. And those little guys, they are the absolute base of the entire ocean food web. If they start to struggle, the ripple effect goes all the way up the chain to the fish like salmon and mackerel that we eat. It's a huge, huge problem. All right, from the sky and the sea, let's bring it back home to the land we live on. This is where the changes often feel the most direct, affecting everything from our food to our homes to the incredible diversity of life around us. Try to wrap your head around this number. 13 million hectares. That's an area of forest roughly the size of Greece. Gone. Not in total. That's what we were losing every single year during that decade. This level of deforestation, especially in the tropics, is a double whammy. It releases massive amounts of stored carbon and wipes out critical habitats. And chopping down trees is just one piece of the puzzle. We're putting the land under intense pressure from all sides. Think about industrial agriculture that strips nutrients from the soil, the way our cities are constantly expanding, and all the mining we do for resources. It all adds up, and it weakens the land's ability to support us. So we've seen what's happening in the air, in the water, and on land. Let's pull it all together. What does the evidence from the last 100 years actually show us? And what are scientists forecasting for the road ahead? Okay, so this isn't a model or a prediction. This is the readout. These are the cold, hard facts measured over the last century. Global temperatures went up, sea levels rose, the amount of snow cover in the northern hemisphere went down, and extreme weather events happened more often. This is the direct, observational evidence of a planet undergoing a major shift. So how in the world do scientists look into the future? Well, it's not a crystal ball. They use incredibly complex computer models. They basically create a few different storylines, what-if scenarios. What if we cut emissions drastically? What if we just keep going as we are? Then they run those scenarios to see the most likely outcomes. And this is what those projections look like. This chart makes it so clear. The future isn't set in stone. It shows us two very different paths. And the one we end up on really depends on the choices we all make starting now. The gap between that low emissions future and the high emissions one is absolutely enormous. And if there's one thing to take away from all this, it's this. Nothing on Earth happens in a vacuum. It's all connected. It's like a giant domino rally. You push one domino over here, like adding CO2 to the air, and it sets off a chain reaction that melts ice over there, which makes the ocean rise way over here. It's one big, interconnected system. So, this all leads us to one final, really important question. The evidence shows we're pushing a key part of our planetary system, the climate, way out of its normal balance. So the question we all have to think about is, what happens to everything else that depends on that balance?